Hello everyone, we continue to chapter 5 economic dispatch of generators. As you remember about the discussion we uh, hold on before, we said that about the load based generation, about hydro generation, large steam turbine, and for uh, fast incoming and outgoing generator we use gas turbine. And we told about the balancing between each generation should be supply loads and losses. And for example, active the power uh, would be generate is divided to load and losses. Actually, the reactive power generated is divided to the reactive power needs for loads and transmission line losses. And after that, we discussed about the limitation of each generator or power plant. The first limitation is about the active power generated or reactive power is limited between maximum and minimum, and it is impossible to suppose that a generator can be generate active and reactive power as a zero. It is not possible, but the generator, the minimum production as P minimum or Q minimum. And after that, we discussed about the steam power plant and gas power plant diagram of generation. And after that, we discussed about uh, how many uh, fuel or energy do you want uh, to produce or supply active power. For example, these curves should be given by the constructor of the power plant. For example, Siemens gives you this curve to determine how many fuel do you need to produce or generate active power. This the vertical axis is about megabtu per hour is needed for produce, for example, P active power. But if we add the vertical axis to a multiplier dollar per megabtu, that is the cost of the special fuel that you need for producing the active power, you get new curve as dollar per hour. For example, for a custom fuel, for example mazout or natural gas, you need a custom dollar per hour for producing active power. And so the heat rate or thermal rate of fuel is depicted as a formula like this. And if you multiple the megabtu multiple this parameter to dollar per megabtu, you get cost function alpha p square plus beta p plus gamma. The gamma is a fixed cost. If you don't produce any power, you have to pay a gamma dollar per hour for only construction or salary of personnel, and we introduce cost function for the cost of a power plant. And after that, if you want to make a derivative of cost function per uh, active power dCF over dP, we have increment of cost function IFC 2 alpha p plus beta. This increment gives us a solution to finding a cost effective and the optimal operation of many power plants together to finding the optimal solution for producing the optimal cost generation of active power in a power systems. And so in a power system that is consists of loads, transmission lines and transformers, there are many generators can be supplied, the loads, transmission line and transformers. So the cost function of the generator number one is alpha p squared plus beta p plus gamma, or and the m for m generator we have m equation. The cost of whole power system with generation or generators would be sigma CFI I from 1 to m, and this cost is called to objective function, and we try to minimum this cost with the scheduling or determining how many active power each generation should be produced or supply for achieving the minimum cost of operation. This equation called as objective function, but constraint is limitation of each generation between minimum and maximum, and we have a equivalent constraint that would be the whole generation would be divided to demand and the losses. This is unequivalent constraint, and it is equivalent constraint. It is the power balance. And so the first scenario is when we ignore the loss of networks and we don't consider any limitation of each generation. So for deterministic and mathematically solving this optimization problem, we consider Lagrangian function. Lagrangian function, or L, is equal to cost plus lambda times of constraint. For example, this cost function plus lambda multiple to the power balanced. The power balanced means that the whole generation is only supply the demand. After that, for solving the Lagrangian, we have to make the change of Lagrangian per each active power generated by each generator, round of lambda over round Pg1, and you make a derivative of Pg1 from the main equation, and this round Lagrangian over round active power should be 0, and so the lambda is determined. We do like this for other generator, and after that we have M equation. we have M equation with M unknown parameter pg1, pg2, or on to pgm, but the lambda is unknown, uh, and on the determined equation is m, but the unknown parameter is m plus 1. And so this equivalent constraint PD minus sigma PGI plus 0 is another equation. So the number of equation is m plus 1. The number of unknown parameter is m plus 1. So after that, the PG1, PGI is equal to lambda minus beta over 2 alpha I. And so for after some mathematical trying or exercise, we have lambda is these equations. These equations only used for scenario number 1. The loss of network is ignored, and we don't consider any limitation of generation. So after that, we try some exercise which is described before in the last sessions, and the next scenario is limitation is considered, but also the plus is deleted or ignored. So for objective function like before, we have equivalent constraint, and also in the second scenario we add unequivalent constraint. So in this exercise we discussed about the second scenario. After the second scenario, we check all generated with the limitation. If the calculated active power generated by each generator was in the each generator limitation, that calculation is okay. But if a calculated active power goes on or goes over the limitation, or goes under that limitation, goes over the maximum or goes down in minimum, you have to set that parameters to the limitation. For example, in this exercise we found that PG1 is about 700 megawatt. The 700 megawatt of PG1 is not true, because the limitation of G1, the maximum is, its maximum is 600, but our calculation would be 700. This means that we have to set PG1 to the maximum and divide other power or economic dispatch between PG2 and PG3. Fortunately, in this exercise, the PG3 goes down from minimum. Its minimum PG3, the minimum is 50 megawatt, but PG3 is 32 megawatt. So you have to set the PG3 at its minimum 50, and the PG1 set at maximum 600, and you obligatory set the PG2 as the maximum and minimum can be subtracted from the whole loads, and Pg2 is determined as 200 megawatts. So in this chapter, in this session, we want to describe about the third scenario. The third scenario says that P loss is not ignored, but there are any limitation for power plants. So in this scenario, we consider losses, but we don't consider limitation. Okay, in this book, in this scenario, the cost function, or OF, is sigma CFI, dollar per hour, but we want to minimize the cost, or minimize the sigma cost function with the constraint of the equivalent constraint PD plus P losses minus sigma of each generator supplying or production of active power of each generator should be 0. This is balance of power balance in presence of losses. Active power balances. PD is the whole load's consumption. P loss is the consumption of losses in transmission lines or other equation, but this sigma is whole generation. So after that, for solving this problem, we also write Lagrangian as before. Sigma cost functions plus lambda, the equivalent constraint for power balancing. And after that, M equation could be right, and after that the balancing is equation number M plus 1. We have M unknown parameters should be determined, plus lambda and lambda, and M plus 1 equation, M plus 1 unknown parameters. In this scenario, you should consider, or you should pay attention about the formula for finding active power losses. The active power losses is a function of generator number 1, that which the active power generated by generator number 2, or number M. So the active losses power is a function of each active which generate by generators. This function would be given in the main questions. And after that, after you calculate round Lagrange over round Pg1, you have to make a derivative of Pg1 in this state, in this term, and make a derivative on the second term, lambda PD plus P loss minus sigma PG1. The PD is fixed. The PG1 can be give you a derivative, but the P loss is a function of PG1, and that makes round P loss over round P1. This is the difference between before scenarios and these scenarios for considering P loss. So when you want to consider P loss in economic dispatch, you have to calculate round P loss over round P1, round P loss over round PGM. So after that, you can make lambda as this question. Lambda is 2 alpha I PGI plus beta I over 1 minus round P loss over round PGI. This is very important for this scenario. This scenario makes us to calculate round P loss over round PGI. We call round P loss we rename or called round P loss over round PGI as ITL. ITL. The ITL is partial loss of networks. ITL is a partial loss of networks. ITL is round P loss as a function of each active power generated by generators over PGI. And 1 over 1 minus ITLI is named PFI. PF means penalty factor. Penalty factor. The penalty factor is 1 over 1 minus sigma round P loss over round PGI. The derivative of P loss over PGI. This is penalty factor. If in final exam we ask you to calculate the penalty factor, you should consider this formula as a penalty factor. The penalty factor is our penalty or losses in cost which we pay for losing the transmission line power. The penalty factor is very important. So another questions. We have two generators in this power systems. The cost function of the first generator is here, and the cost function of second generator, the all cost function is the dollar per hour. The round of cost function over the round PG1, the derivative of cost function number 1 over PG1 is here. The round of cost function over round the active generator bar generator number 2 is lambda is here. This is very simple. And the balancing of PD minus whole generation would be 0. The balancing of power would be 0, and so this equation number 1, this equation number 2, and this equation number 3, and after that we have a special formula for finding PG1 and PG2 and lambda. This calculation is based on, we have no limitation, no limitation, and no transmission line losses. It is very simple. We discussed on it before, and its equation or the procedure of solving is very simple. So after that, we discussed over a two generator in a transmission lines. Its cost function is here, but the limitation of each generator is between 10 megawatts over to 100 megawatts each generator. But the PD is depicted here. It is almost the real case. From midnight to 6 a.m. we have 50 megawatts 6 a.m. to noon, 100 megawatt, 3 p.m. 125 megawatt, 6 p.m. to 6 p.m. we have 200 megawatt, 10 p.m. to 10 p.m. we have 150 megawatt, and 10 p.m. to midnight we have 50 megawatts. This the changing of demand or loads, and so we write IFC 1 and 2, and for the time between 12 a.m. to 0 to 6 a.m. the whole PD is 50 megawatt. And after solving this problem, the PG1, PG2 and lambda is determined, and all achievements or calculation are in limitation. After that, for 6 a.m. to noon, the PD is 100 megawatt, and the calculation is here. And after that, for other period of time, we have to write, and we say that we can consider that in 3 p.m. to 6 p.m. we achieve that our calculation is 107 megawatts. This exceed from the maximum limitation, so we change PG1 as 100 megawatts, and so PG2 have to be 100 megawatt. Please consider each limitations. Another exercise. Another exercise is about the last scenario we discussed about the P loss or loss of networks. We have three power plant G1, G2, G3. It's kind of full. Is here gas mazout or coal stone. The cost of fuel dollar per megabit BTU and the megabtu per hour is H1, H2, H3, and the maximum and minimum power which each generator can be produced or supply. The first action is multiplying the R multiplier to H. For multiplying this column to this column, you find cost function. The cost function is R multiplier of R multiple to H, and the cost function is determined. After that, you have to consider P loss. According to the course or the last scenario we discussed, the round cost function over round PG1 plus lambda multiple to round P loss over round PG1 minus 1 should be 0, and you after that add the last equation of power balancing PD plus P loss minus sigma PGI should be 0. And so after making derivative of these four equations, we gives or we achieve these four equations. We have four equations and four unknown parameters. After solving these four equations, we find that PG1 is 434 megawatt and PG1 is in range. PG2 is about 300 megawatt is in range, but P3 is 130 megawatt is in range. Fortunately, lambda is $9.5 per megawatt hour. The rate of cost function per megawatt hour energies. So after finding PG1, PG2 and PG3, after solving these four equations, you have to calculate P loss. P loss is these equations, and you should substitute the PG1 to PG3 in these equations for finding P loss. The P loss is 15.83 megawatts. Please try this exercise in your home by your calculator yourself. It is very important. Another exercise is about three power plants with the cost function is written here. There is no limitation of power generated or P loss. So the P loss and limitation of the generation is ignored. So the PD in 24 hours is divided like this. From midnight to 10 a.m. is 200 megawatt. Another period is 500 megawatt, and the 4 hours from 20 p.m. to noon is 300 megawatt. So for each period of time and each period of PD, you have to write its equation of derivative here and the balancing of active power like this. Please pay attention. We don't consider P loss in this exercise. And after that, for the T between 0 and 10 a.m., the PD is 200. The PG1, PG2, PG3 is determined. We have don't consider any limitation. The lambda is here. After that, for this period of time, we calculate the PG1, PG2, and PG3, and for the last period of time, 20 p.m. to midnight, we have PG1, PG2, and PG3 and lambda. So we can depict that the lambda could be in the first period is 9.2, the second period 9.7, and the last period 9.4. And we can see that this period you have to pay much than other periods for supplying power. In each generator we have this dispatching, for example PG1, PG2 and PG3. The first period, the second period, the third period of generator 1, first, second, and the third period of generation in power plant number 2, and the first 2 and 3 generation of power plant number 3. So in the final exam I realized that finding the solution of the losses is not easy, but finding this set of equations, especially please pay attention, especially losses and making the parameter squares, is a nonlinear problem, and I don't expect to calculate this set of equation in your final exam, but the correctly writing of this set of equation is very important. Please pay attention. So after solving many problems about the economic dispatch in this chapter 7, we finished this chapter, and thank you very much.